Hi everyone, so in this video we're going to introduce the second law of thermodynamics, and it is based on this idea of entropy, which we usually write as the letter S, and it represents the total disorder in a given system. Total disorder in a system. Now, this disorder can be computed in a couple of different ways. We can think of it in terms of vibrational disorder. So we can have atoms that are vibrating in various directions in 3 dimensions. And so those vibrations add a certain amount of disorder. But then that disorder can also be configurational. And so when we say configurational, that's just a fancy way of saying that if we have some atoms, how many different ways can we arrange them in a certain pattern? So here we've got a pattern of 9 atoms. How many ways can we mix and match? I'm going to look at that a little bit later. But first, before we do that, let's erase the chalkboard and look at how the second law is most often expressed. So in the early days, one way of thinking about the second law in the 19th century was like this. Let's say we had some material that was sitting at a very, very hot temperature. And I'll just draw this material in the shape of a cube. And let's say that that material that is sitting at high temperature is next to something that is at a much colder temperature. So we'll draw another cube over here. And so there is our stuff that is cool. It is sitting next to stuff that is hot. So which way is temperature going to flow? Well, we knew from early experiments and really from common sense, you'd expect that heat, so Q is equal to heat, that heat would flow in this direction from hot to cold. That we would take heat, whatever that thing was in the 19th century, they were really not very sure of what exactly it was, but they knew that it would flow in this direction from hot to cold. So the first expression of what we call the second law of thermodynamics is that heat will flow from hot objects to cold objects and not vice versa, so long as there are no other forces acting on the system. Now, the way that that expression eventually evolved would be to say that for any reaction to occur spontaneously, for any reaction that is spontaneous, then what we mean is that entropy would increase. And for any reaction being spontaneous, what we really mean is that there are no external forces acting on the system to push it in one direction or another. So take away any external forces and how will a system naturally move? And it'll do so in a way that entropy will increase, not stay the same or decrease. So another way of thinking about the second law is that it provides kind of an arrow on time. People have thought about time from the concept of entropy. Time is a direction in which entropy increases. All right. So with the advent of the atomic theory, a fellow by the name of Boltzmann came up with another way of thinking about entropy, and he came up with what we now call Boltzmann's law. So entropy is equal to this thing called Boltzmann's constant. So that's a T there, Boltzmann, and that's Boltzmann's constant. It's not a large number, it's a very small number. It's 1.3806 times 10 to the minus 23 joules per Kelvin. So that is the proportionality constant that equates entropy, this thing here, with this fellow here, omega. And so what is omega? Omega is the number of total possible states of a system. How many ways can we configure a system? And when we think about how many atoms are even in a very small amount of material, this number begins to become very large. So solids have a very ordered atomic arrangement by definition. All minerals would have an ordered atomic arrangement. That would be a limited level of entropy because there's only a limited way you can arrange those atoms. But if you take those 8 atoms and you were to heat them up to the melting point, now they'll fill the same space, so you'd have the same volume, but those 8 atoms would be free to move around. So let's see, 4, 5, 6, 7, 8. So imagine 8 items now. 8 atoms filling that space, but doing so in any place instead of just at the corners. And so that is the case if you have something that is liquid. So over here we have a mineral. We heat it up to the point where we have a liquid. And then if we heat it up to the point where we boil it and we have vapor, now those 8 atoms are no longer restricted to any particular size container. They can move out in all directions. So this would have a very low entropy. We'll write a small s. This will have a larger entropy. And this will have a huge entropy. And one of the ways to think about how these would be quantitatively different would be to use Boltzmann's law.